Okay. So I thought today we would start um, just talking about the diode. And I'm going to talk about it in an intuitive way, which which I might call job interview style, but it's really kind of how I think about things when I'm trying to come up with something new. Equations are absolutely important, and you need to be able to derive and do whatever you need to do. Um, if you can come up with an analytical equation for it, you can change a parameter and get, like, let's say this resistance varies by 10%. All right, what is that? What is the voltage range going to be if I just on a simple voltage divider, right? So okay, this is the P side, and that's the N, or it could be N plus P or P N or P plus and N plus. And while there might be ranges of these, right, really all they're saying is that this is more highly doped than that. Okay. Oh, take care, Mariel. If you got to go, you got to go. So what this would say is that the junctions are relatively equal in doping. Um, and so let's just draw a quick energy band diagram, and thermal equilibrium is the easiest thing to do. So I just draw the Fermi level first, right? This isn't bending at all, so there's no Fermi level straight. So for the first one, P plus, right, the valence band is going to be close to the Fermi level. I'm going to put it very close, right? And then that's N-type doping. So it's not as close. I'm just going to make it a little bit higher, okay? And then you know what? I am sorry. It's been a while since I've, okay? This is the band gap. This is a lot closer to the Fermi level than this, so that makes it P plus. There's our band bending, right? And were I to draw the junction, right, it would be much closer to the P plus side, right? So if this is the depletion width, okay, it's mostly on the N side. Now, just to think about it is that we have a lot of extra holes here, right? They're going to diffuse because things diffuse when there's a high concentration gradient, right? So if I have a lot of perfume in a bottle, it's going to diffuse out of the bottle, right? So I have a lot of holes, and they're going to diffuse where there's less holes. I have a lot of electrons, right? And they're going to diffuse to where there's holes, right? And they recombine. But the holes have to, because there's so many compared to the N-type, right? They have farther to go, right? And then let's just talk about capacitance. We'll call CJ, right? This depletion region, right? That's an insulator, right? There's no charges in there because the electrons and holes have recombined, right? So Capacitance is just some area times a dielectric. In this case, it's silicon, or it could be silicon carbide or whatever. And that this, of course, as you know, changes with voltage, right? When I apply a forward bias, the depletion width gets smaller because these bands come closer together, and in reverse bias, it's the opposite. And so you can control the capacitance with a voltage. And some doping profiles lend themselves better to that. All right. But the big thing is that at thermal equilibrium, you have a current due to drift, right? That's the electric field. And that equals the current equal to diffusion. That's these electrons and holes going. And so they equal each other, right? But this drift is caused by the electron gradient and the hole gradient, all right? So that drift is caused because an electric field is created because of that. Now, so there's a lot that's going on here. There's a lot of different effects, right? But, you know, kind of a 128 way of looking at it. Is that equation here. Now, none of these things really show up on the data sheet, okay? Now, in a SPICE file, you will get various capacitance parameters. You won't you won't get the area, but they'll kind of lump some things in where all you have to do is multiply it by the area, or sometimes even a perimeter, because you know the depth of something. All right. And so a lot of the SPICE files, right, for a MOSFET aren't actually the MOS capacitor part. It's all based on the diode. Same with the BJT. All right. But this thing here, ideality factor, it has to do with what kind of current is dominating. Is it a drift? Or let's just say, what kind of recombination process is dominating? And there's not really an equation. You really just have to kind of go and measure it. Now, yeah, depending on what kind of semiconductor, you can be assured that it'll be N will be greater or smaller, and on the doping. But really, now, yeah, in a diode SPICE file, you will find this, and you will find this, and you will find some capacitance values. All right. But, oh, sorry. Uh-oh. God damn it.
We're still seeing you, Professor. I don't know if you can hear us.
Hey, sorry, I kicked myself out of the meeting. And
Still
now I
able.
see the chat question. Yeah, let me just come back. It can be done different ways, but usually it's VTH, and that's thermal voltage, and that's KT divided by Q, which is around 26 millivolts or electron volts. And you have to be careful because sometimes the K has already got the Q in it, And so, all right, I always use, what is it, 1.38 times 10 to the minus 23, temperature in Kelvin, right? 300 is like room temperature. And Q is 1.6 times 10 to the minus 19 coulombs, right? So that's all that is, okay? So, and yeah, what would an exam question in 128 be is I would have these things, and then I would have energy band diagrams, and you just had to figure out which one was which, right? When they're equal, the junction's in the middle, right? And so these are two, and how would you tell the difference? Is this one, the junction would be bigger than that one, right? And then these, you can just figure it out from there, right? But this idea of having a highly doped junction and a lowly doped junction is actually really important in MOSFETs. And before I get on to the just move it to here, is that, yeah, MOSFET, N plus, P, N plus, right? Some metal there, we can call that the source. Some metal here, we can call that the drain. And if there's some oxide, right, we can put a gate, right? Well, the thing is the whole reason why that MOSFET works is that you have back-to-back diodes, right? And, right, if a diode blocks current, right, and they're back-to-back like this, there should be zero current, right? Except it'll break down one way or the other, okay? Well, the thing is the depletion width creeps in here. And the larger I make VD, right, this, we'll call that VDS for some positive gate. This creeps in, right? And so the channel length keeps getting smaller the larger this is. So let's say we're already in saturation. Ideally, right, that'd be flat, right? And if we look at the equation for current, we have W divided by L, some transconductance term, and then some voltages, right? Well, this is actually a function of VDS, right? And so it creeps up. And that slope is related to the output resistance, and which really controls the gain. Now, again, kind of assuming you've had all the courses, but for a common source MOS amplifier, you have minus GM, right? And you have your output resistance, which then would be in parallel with some bias resistor, right? And I might be forgetting something here. I didn't really have it, but really, the higher that, right, the greater the slope, the smaller that resistance, the less gain you can get. And so you play with, so a device physicist would play with this doping structure to try to not make that happen, okay? So in 124, that's really important because you're doing analog circuits. Digital circuits, not so much, because you're just going full on and full off, and the more current, the better, in general. Okay. And I guess, I don't know, this version of Zoom isn't letting me know. Oh, if I put a minus VD, that's incorrect. sorry, that's my 110 creeping in because everything is exponential decay. I equals I naught e to the VD. And yeah, sorry about that. I used to never do that before I taught 110. All right, because it's exponential increase. Okay. Thanks for catching that. And you just have it shout out because the other machine, my other computer would kind of pop up more of a message if there was a chat. Okay. All right. So what I thought, that's kind of very, introductory theory, but that's really how I think is like it's all about the diode, and that diode depletion width is creeping into your active region and increasing the current, right? And yeah, in a high power device, right, if I put 100 volts on here, it might push this all the way here and it touches and shorts, right? To where it's not showing much, but the current can all of a sudden just go like that. Or sometimes the diode just breaks down, right? Okay. So we have 3 diodes, all right? This is a MOSFET, right? And even though it's a MOSFET, an NMOS is an NPN structure, right? Which is kind of like a BJT, whether you want it or not, right? Now they process the substrate to make sure that it doesn't act like a BJT. And here's a diode, PN. Now, if I recall, the actual diode is N plus P, all right? And then here's a BJT, and it's actually an NPN, but rather than controlling the current flow by inverting a channel, you're actually injecting electrons across with this device here. And I'm just going to leave it there for right now. So actually, I wanted to extract some values or just show you how. So I'll just run that. And there's 3 currents. So we have the source current, we have the diode current, and then we have the base current. All right. And actually, you see, this is actually linear right now, not exponential, right? And this is linear here, and that's exponential. So in fact, to actually really see what's going on, right, you have to look at things in the log domain or logarithmic, okay? Now you can really see what's happening, right? And so we're talking about forward bias. And so E to the VD and thermal voltage is much bigger than 1, right? But there's this thing not usually done in undergraduates, but it's minus IDRS, which now makes it like not analytical. You have to solve for it numerically. And so the bigger the ID, the more the voltage, whatever I apply, more of it is falling across that resistor. All right, and that's really what's going on here. So you can see a straight line in the logarithmic region. That means, we're really approximating it as this. So in forward bias, yeah, it's I naught. And we can extract this and this from the forward bias region. All right. What happened? Oh, nuts. Well, I'm sorry, we're running a little bit out of time. I'm just gonna so I'm just going to hand draw this. All right. So if this is VD, and now the important thing is it's log, natural log of ID. You'll get kind of this thing. And what you do is you just take 2 points, right? And you find the slope, right? And then you find the x-axis intercept, right? Because if I take the log, natural log of this, right, I get right. And so this becomes that, right? And the slope is that. And you can go, if some of the details you can actually see. So if I go for a diode, let's just do a diode. If I pick a new diode, well, there's the IS, I called it IO, and you should get a reasonable result. You tend to need a lot of significant figures for it to work though. And then there's the N, and then there's your capacitance value, junction, right? And so, and there's a way to extract that as well. I'm just not going to go over it today. And then there's some other things, but you can go and that's how those things are found. Okay. So that's just today, because I had heard that some people wanted to talk about diodes. Next week, I can talk about stochastic resonance or go more into, actually, I can show you how to generate a spice deck, even a simple one, let's say. Or whatever you guys want, you just let me know. Okay. Any questions or anything or comments or?
Thank you, Professor.
Professor, how the capacitance look like? Can you hear me?
Okay. I know, I said this is a research club, but there's more things going on than just that. That's why I started with that review. But it's not like 110 where I'm told what I need to cover a certain amount of things. This is more for fun, to keep engaged and to get prepared and all that. So really, just let me know, okay? I can't hear you.
I have a question. How the capacitance look like on the Diode?
Why can't I hear you? That's not good. Oh. Thanks, Alex.
Gilbert, try again now.
Yeah, I can hear you now.
Yeah, I was saying, how does the capacitance look like inside the diode?
How does the capacitance look? I'm not quite sure.
Yeah, how? Because you're talking about capacitance inside the diode, and I'm wondering how it's look like.
Okay, let me share the screen again. I'm a little confused at look like that phrase. Let me think about it, and you tell me if. Let's see, I'll share again. Oh. Okay. So let's just talk about a normal capacitance, right? I'll try to draw it in 3D, right? Right, let's just call that metal, right? And we'll call that metal. And in between, you have a dielectric, right? You know, if I have two pieces of aluminum foil separated by a distance, right? The dielectric could be air, could be vacuum. Or in this case, it's actually silicon. So when you have like two conducting things with charge, right, separated by something that doesn't conduct, right, an insulator, right, you get a capacitor, right? And the normal capacitance equals the area times the dielectric, right? So air is close to 1, vacuum's even better. Silicon is 11.9. Silicon dioxide is 3.9, and that's relative, right? ER times 8.85 times 10 per centimeter, right? And then you have your distance, right? So that's like this two-dimensional thing, right? And so now I'm going to try to draw the band diagram sideways, if you will. Okay. Oops. Okay. So this is, I'm just going to call it P-type silicon semiconductor. So that's acting like, and we'll give it air quotes, a metal. This is, I'll just call it N plus silicon. That's acting like a metal. Now remember, this is just one dimensional, right? And so here, I have all these holes diffusing this way. I have all these electrons diffusing this way. And in here, they recombine, right? And so now it's actually an insulator, except we don't call it D, we call it width, okay? So that width actually changes with voltage. If you've taken 128, the equations are right there in the book, right? Did that answer your question?
Yeah, I was looking the first picture like a capacitor referred to the capacitor, and the second one referred to the diode, right? Oh,
Well, here's the thing. Good question. The diode is a capacitor, or it has capacitance. Okay. That diode has capacitance associated with it. It has resistance associated with it. The thing is the diode is kind of weird because the diode bit is right here. However, the electrons go here in forward bias, right? And they recombine. So there's something out past here where the electrons are recombining with the holes, and here the holes are recombining with the electrons, right? And then there's some statistical average length that happens, right? And then after that, well, then you just have a bar of silicon effectively, and it acts like a resistance, right? So, and then like even here, right? If I have a wire to the capacitor, the wire has a resistance. There's an interface resistance. So there's all these resistances that a real diode has. Even though in this diagram there is a resistance, one never talks about it because when you're trying to understand the diode, putting in the resistance is a little bit too hard at that time, right? But also, if this were a direct band gap semiconductor, that diode is also an LED. And then there's a hack where you have an LED and you can bias it such that it acts like a photodetector too. Okay, so is one of these things is, and I'll just use the MOSFET example, N plus P, N plus, right? Source, drain, gate. So the thing is you look at that and you're taking your 122 to 128 final and you say that's a MOSFET. But it's also two diodes. It's also a MOS capacitor. It's also got resistances. These diodes have capacitance. This, of course, has capacitance as well. And here's the thing. Normally, they say, how fast can you switch that MOSFET off and on? Oh, how long does it take an electron to get across? And that's true. That is the fundamental limit. But it is the capacitances on this diodes that is the true limit of switching a CMOS circuit, right? The bigger that capacitor is, the more energy it's going to take to charge and discharge, and the longer it'll take. A digital circuit is certainly non-linear, and the capacitances and everything is changing with voltage, but really, there's simple exponential decay things for how long it takes a thing to turn off and on. Okay, does that help?
yes, good. Thank
Okay. Anybody else? That was a great question. Now that I can hear you. Okay.
So how are we going to be doing? Are we going to be meeting just like you just going to send a link, or we have friend time, or how the
Okay.
project?
So yeah, this link, I actually now like I am gonna go on vacation, but I made a link for 11 o'clock every Saturday until school begins, I think. No, I can't always make it. But the thing is I can make you guys hosts and you can meet, right? And I do want to have somebody give a talk to you. I was able to get these things donated, but the guy who uses them will give us a talk on how to use them. And it's not device physics, but it's a programmable, it's like a microcontroller, an FPGA, and some analog things all rolled into one. It's pretty neat. And yeah, given a little more time, I might have used this in 110 lab, but I ran out of time, and that's that. But yeah, I'll send out a message. Hey guys, yeah, I can meet, or let's do this. But what I'm saying is you can tell me what you want. And if it's something that aligns and we're all agreed, no, we can do it. Okay. This is like a club. I'm not the president. I'm just a helper. Okay.
Sounds good.
So-
In the middle there for a minute when you thought you dropped off Zoom, by the way, I think I could still see your screen just in case you want to cut it out because it had your email.
Was there bad emails or something?
Not that I noticed, just I didn't look that hard.
You know, I think what I'll do is, yeah, I'll take a look. I don't know if I was swearing or anything. Like, what the hell happened? So, but I'll take a look at it. Yeah, thanks for the heads up.
And
And actually, if you want to talk after this, Alex, I have some time.
okay.
Yeah.
A question I had, so I was following all this and it looks like kind of in general what you were explaining is how to find these values with respect to a diode. Like if I was going to use it in something directly, some of those values wouldn't be explicitly available. I'd have to test for them. Does that sound right?
Yeah. Well, here's the thing. So if you have a spice deck, they're there, right? But they're not on a data sheet. And so sometimes it's like, hey, where do I look this up on the data sheet? Well, it's not there. They'll give some things, and sometimes like for an LED, they'll say, here's an ID-VD pair, which will, so the LED will be turned on if you set the current to 10 milliamps and the voltage to, 1 volt, right? So all you just pick your power supply and a resistor to make that happen. Okay. Sometimes what they'll show is they'll actually have a curve, an ID-VDS curve in the log fashion that I was showing you, so that you can pick items off, right? But there'll be other things like power limitations and a lot of other things. But a spice deck that you use to actually design the inside of an op amp, it's there.
Okay.
You can estimate, but sometimes it's like, here's this number, where did it come from, right? And I used to get this question a lot in 128. I see a spice deck, but where do those numbers come from? And like, and so that was just kind of an introduction to that. And again, but like if you wanted to work with Professor Hugh Wong, right? He's working on silicon carbide FinFETs, I think, right? So there's still diodes and MOSFETs and all of that. It's just kind of an advanced structure. And so he's actually doing research with the students right now, simulating it in a fancy tool, which actually I can show you one time too, called TCAD, where you just set the physical structure up, apply voltages, and see what happens. But in order to understand that tool, all those things they talk about in 128 become important, like mobility reduction, velocity saturation. All those terms are actual flags that you turn off and on to get your simulation to work. I'm not trying to get rid of anybody. It's just, I knew he was working with somebody, but now I realize he's working with a lot of people, and kind of, he might be the new guy, but I'm kind of inspired by him.
I think I keep hearing Spice Deck. What's
Yes,
that?
right. Oh,
Just LT Spice simulations or?
yeah, yeah. God, thank you, because that is a jargon term, right? So here, so this is this part here, right? Dot model 1N 194D, all these numbers, the IS, RS, N, CGO, that's the Spice deck.
Oh, okay, DECK.
Yeah, which,
Okay, thank you.
but maybe to help you remember, let me try to find a better example. No, it's just funny because the deck, I think it's because things used to not be graphical, right? No. It was all based on text, and you'd have this whole list of things. Maybe this one. Yeah, here we go. So this is a part that you use in 124. I think you still do. So dot model, what is it in NMOS? What's the name of it? What level of spice? And then all these parameters are what go into making you get the correct voltage and current. And notice there's 1, 2, 3 capacitances, right? And then there's these other things that go with capacitance that allow you to calculate. It allows the spice deck to actually calculate the capacitance. And this is a, what is this? Yeah, I'm still sharing. Well, this, what I'm showing you actually is just a common source amplifier biased with a current mirror, which that's a 124 thing. You stop using resistors, except for this one right here, and you start using things called current sources. And that current source, the higher the resistance, right, the more ideal it is. And that comes back, but those things are all based on transistors, right? And that diode, when you apply a reverse bias, shrinks the channel length, right? And you get this here. So the better job you can do for not making the channel, the depletion width go into the channel, but go back into the drain side, the smaller you can get that. And yeah, there's this, there's a structure. You can have N plus N P N plus and this is oxide, and the channel is right here. And so this is the drain, and so it's actually less doped than the body, and it goes here. And so you can get really high resistances, right? Which tend to be how these power MOSFETs, if we just, right, these are all discrete MOSFETs that you just buy. They're not part of a chip, right? VDS 30 volts, 240 volts, right? That's pretty good. But it's, yeah, the oxide thickness has to be thick enough to withstand a large voltage, but a lot of your work is done trying to get the diode not to, well, not to be a pill. It's not necessarily the best way to say it, but okay, that's a great question. And, maybe I'll just have the link available rather than put it on my public channel, because it's not really ready for prime time anyway. Okay.
Sounds
Well,
good. Thank you.
all right. I think that's about what I have for now. Alex needed to tell me something. So if you guys could pop off and, just let me know what you want to go over next week.
So one more quick question.
Yeah.
By doing what we be gonna be doing in the midterm, when you have a project, I think it's a manual.
You can work on that project right now if you want. Maybe I'll introduce that project next week.
Yeah, okay.
Okay. Yeah. Take care. Nice to see you. Yeah. Take care, Sahil. Hey, Alex. Oh, you're muted.
I think you're still recording.
Oh, Jesus.